In this video, we'll study the equations that we can write for spheres. But before we go to spheres, let me just step down one direction to 2D and consider circles, which I hope you all know that the equation for the circle of radius r centered at the point C, which has coordinates C1 and C2, is x minus C1 squared plus y minus C2 squared equals r squared. Okay, so points in the coordinate plane, the Cartesian coordinate system with coordinates x and y that solve this equation, those points lie on the circle, which has its center at C, and its radius is equal to r units. So, of course, we can rearrange this equation using vector notation. So this is the difference of two vectors, C1, the vector x, y, and the vector C1, C2. And of course, what we have there is, on the left-hand side, is basically the length of this difference squared. This is how we get the first coordinate squared plus the second coordinate squared. This should be equal to r squared. So, of course, we can, again, rewrite this by setting the point xy to be an arbitrary point on the circle, so a position vector from O to some arbitrary point on the circle Q, and this vector is, of course, points to the center of the circle, so C1, C2 is equal to OC. This gives us yet another way of writing this equation, which is the vector OQ minus the vector OC should have the difference of length r squared. Difference should have the squared length of r squared, or just the length of r. And this is the best way to capture what we mean. I think this is the most intuitive. We are looking at points which are of an r distance away from the fixed center. But of course, this is the equation that you are probably familiar with, and this is also a useful way of writing this. But the point is that these two equations are basically the same thing. One uses vectors and the other one is using coordinates. Now, similarly to all this, we can talk about spheres. For spheres, we have the following equation. X minus, let's call it C1 again, squared, plus y minus C2 squared. Now, this is where we step into the third dimension. Z minus C3 squared should be equal to r squared, where the point C, which has coordinates C1, C2, and C3, is the center of our sphere, and r is the radius. Now, again, just like we did before, we can go through the same sort of calculation and see that this indeed just means that we have an arbitrary point in space, Q, the coordinates x, y, z. It will be on the surface of this sphere if the distance of, or the length of the difference of these two vectors OQ and OC is equal to R. So this is why you see it's a very good way of writing it, because it's the same thing in no matter what dimension you are considering. So this is another vector way of expressing, writing the equation for a sphere. Before we finish, I would like us to have a definition. So a tangent plane, by a tangent plane, to, let's call that, let's have the notation S for that, to a sphere, let's call the sphere sigma, is a plane that touches sigma at a unique point, at a single point. So they only have one common point, this tangent plane and the sphere. Okay, let me quickly draw a diagram, well, a figure for you. So here is a sphere, and we look at one of its points, and you can imagine putting a plane to that point. That would be our tangent plane to this sphere, and they only touch at that one single point. Okay, before we finish, I would like you to solve the following, to answer the following question. So my question is, where does the following sphere intersect the x-axis? So if I take the sphere with center, so where does the sphere of radius, let's say of radius 3 and it's centered at the point 0, 2, -1. So where does this sphere intersect the x-axis? So this is my question. I want you to pause the video, calculate the intersection point, and use the box below to input your answer. Okay, I hope you paused it. And first of all, in order to find this intersection point, we have to have an equation for the sphere, and that equation looks as follows. It's x minus 0 squared, so that's just x squared, plus y minus 2 squared, plus z minus 1 squared, that's z plus 1 squared, equals the radius squared, so that's 9. So the x-axis, so this is our sphere, let's call this sigma, and the x-axis consists of points which have only an x coordinate that is non-zero, that can be non-zero. Of course, the origin is also in the x-axis, so 0, 0, 0, 0 could be one of these points, but the x-axis consists of these points, and let me use a parameter instead, s, with s being a real number. Now I want to find the intersection points of these two objects, the sphere and the x-axis. What I have to solve is this system of equations. If I just plug in for x, y, and z, s, 0, and 0 into the equation of the sphere, I will find that it's s squared plus 2 squared plus 1 squared equals 9, which is the same thing as saying s squared equals 4, because it's s squared plus 5 equals 9, so the s squared equals 4, which means that s should be equal to plus or minus 2. Okay, so the intersection points are the following: 2, 0, 0, and -2, 0, 0. Okay, I hope you got it right, and I'll see you in the next one.